Hey guys, welcome. Yeah, so I hope you're having a great day, and I also hope that you've been watching and enjoying this video series on partial derivatives. And in particular, if you really want to understand partial derivatives and you want to know where they come from, and you want to know how they're related to derivatives of the old, like Calc 1, or introductory calculus, then watch example 0. Example 0 is the big picture on partial derivatives, explaining all of what I just said, answering all those questions. Yeah? Okay, cool. Now, in the last example, example 2, we saw that there's such a thing as that. The partial with respect to x, and then again, the partial with respect to x of that. So the partial with respect to x of the partial with respect to x. We also saw that there's such a thing as this. And so then, what's begging is a question, does this make sense? And the answer is yes. It's called a mixed partial. Because, well, if you have this is xx, clearly that's not a mixed partial. Whereas this is a mixed partial, it's x and y, right? And it turns out that by Clairaut's theorem, which is sometimes in books called Young's theorem, fxy is equal to fyx so long as these two partial derivatives are continuous inside of some disk D. And so this will be true for any point AB and the disk D, where again these two partial derivatives, second partials, are continuous in that disk. Yeah? Okay, so we're saying it's not always true. So if this here, fxy, is not continuous, or fyx is not continuous, then Clairaut's theorem, a.k.a. Young's theorem, sometimes called mixed partial rule, and this is like for everyone who dislikes Clairaut and Young, I suppose that's who calls it mixed partial rule. But yeah, like not a misnomer, right? Because it deals with mixed partials. Okay, now in our final example, example 4, we will state a stronger case or a stronger version of Clairaut's theorem. So that will perhaps be our final video, but what on partial derivatives. Okay, but why don't we check that this is true on a specific example, so that way we feel a little bit more satisfied. So let's say fxy is equal to x squared y cubed plus 3xy. Actually, let's say pi xy. Let's make life a little bit more interesting, right? Okay, so fx, the partial with respect to x, another practice on partial derivatives, is going to be, well, treat everything that's not an x as a constant. So that means that we go 2x y cubed plus pi y, right? On the other hand, if we did fy, right, that means treat everything that's not y as a constant, so treat the x and the constants as constants. That'd be 3x squared y squared plus pi x. Well, okay, so far they're not looking very much alike. So is this really going to happen? That is, if we do fxy, which is we do the partial with respect to y of this, what do we get? If we do fxy, then this time, since we're taking the partial with respect to y of this, we treat anything that's not y as a constant. So 2x is a constant, but yeah, we start with 6 xy squared, and then plus, clearly pi is a constant, so the y goes away, we just get this. Moment of truth. So this best end up in the same place if Clairaut and Young ain't lying, right? So fyx. Well, what's that? So over here, we treat the y's and the constants as constants. So that'd mean, well, 6x y squared, and then plus pi, right? 6x y squared plus pi, 6x y squared plus pi. So we are happy. Okay, as I said, and the next video is mixed partial stronger case, rather Clairaut's theorem stronger case, stronger version of Clairaut's theorem. Sorry guys. I hope you enjoyed this, and yeah, keep watching. Take care.